Welcome to Slope Reliability, the show where we learn about reliability, observability, and resilience one day at a time. I'm your host, Stephen Townsend. Welcome back to Slope Reliability. I'm Stephen Townsend, and this is the show where we learn about reliability and observability and resilience one week at a time. Today, Michelle Casey is back. How are you going, Michelle?
Yeah, I'm pretty good, thanks. How are you?
I am pretty good. It's been a weird time. I spent the weekend back at my mum's place in Blenheim, going through all of these letters and papers and trinkets from my teenage years and early university. It's just been a weird time. Reminiscing.
It can be quite interesting and nostalgic looking back at that stuff, right? I did that last year, and I remember feeling like my grades were way worse than they were, for example, which was really odd.
I just keep getting this feeling of there was something about that time, especially drama school after uni. There's things there that I've lost as I've got older, but there's also lots of things that I've gained, and I guess that's the reflection for me. Yeah.
Interesting.
Yeah. So you were the first person to introduce me to the concept of resilience engineering, and I hadn't really heard of it before. And one of the things I've struggled with, and I know this is fine, did a session about it recently, is how do you define it? And it's not as simple as just putting a few words down and going, this is what it is, and having understanding. So what we thought we'd try to do today is an introduction to resilience engineering. And Michelle has done a huge amount of work sort of pulling together the different ways we could go through this. And I think it's brilliant. And you had some review and some help from someone, is that right?
Yeah, it's now. So John Allsper reviewed the episode outline just to make sure it was correct. So thanks, John. Appreciate your review and feedback.
Thanks, John. So to kick things off, let's start with what is resilience engineering and where did it come from? Because it didn't come from technology and software, did it? It came from other places.
Yeah, no, that's right. So resilience engineering is an interdisciplinary scientific field and a community of researchers and practitioners with diverse backgrounds working in many domains. So I think that's often overlooked when explaining resilience engineering, and some people think that's kind of the most important part. So resilience engineering emerged from safety science and human factors and came from other, usually higher consequence industries into software. So industries like nuclear power, aviation, and healthcare. It draws a lot on systems thinking and particularly focuses on complex systems and cognitive work and human performance in the context of complex systems. Mm-hmm. And it provides an alternative perspective to the idea of human error.
Yeah, I think it's those high stakes industries like medicine and aviation. I've heard conversations and discussions about, well, is software that important? And I guess it depends on the software, right? But I think when you talk some of the systems now that we talk about, just the number of people that are impacted, if there is with the lack of resilience, it adds up. The volumes of money that can be lost, which I know it's just money, but.
I mean, you're working in insurance. I mean, I'm consulting, but I'm working with kind of like product tech companies. And so I can see perhaps people don't necessarily die for our software incidents, but there are kind of instances where that could be the case. So, yeah.
So there's three different terms that you've sort of elaborated on here, and I might help describe the difference, because I thought, and I imagine many people out there just think of resilience as another word for reliability. But you've got these three terms: reliability, robustness, and resilience. So what's the difference? Let's start with, yeah.
What are they? It's funny you say that, because I was reading an old blog post I wrote several years ago, and I'd used the word resilience and I should have used the word robustness, but at the time I wrote it, I didn't know that. But getting onto the definitions, I think I have to credit Tim Nicholas, who's a former colleague of mine, for these definitions, and he also heavily influenced my understanding of resilience engineering. They also come from, I guess, Dr. David Woods, and the paper is called Four Concepts of Resilience. So that's, I guess, where it kind of heavily influences these definitions, as well as quite a few talks by John Allsper. So the definitions we're going to use are kind of the scientific definitions that are used across industries. So reliability. Starting there, reliability should be considered an outcome rather than a state. So we can only determine if a system has been reliable after the fact or in retrospect. So after a system has faced a particular hazard or challenge, after we've had an incident. Things that have happened in the past define the set of conditions or parameters that we use to assess reliability. So past incidents often have a really big impact on how we assess reliability.
So does that mean if I'm going to say this is a reliable system, I'm saying that based on historic precedent, not because of any quality?
Based off your historical understanding of the types of incidents that have happened in the past, probably the work that you've done to improve the kind of quote marks reliability, and how reliable you think the system is based on all of that.
Interesting. Which almost seems problematic because the history doesn't necessarily foretell the future as well. So just saying it's reliable or saying it has been reliable doesn't necessarily mean that it will be reliable. Anyway.
Yes, kind of, yes. Well, we go through the other definitions, right? So we move on to robustness. Robustness is the ability of the system to continue to operate as intended in the face of known hazards or challenges. So if we build our system in a way that means it can cope with a particular challenge or hazard, we can say that the system is robust to that challenge. So it's about known hazards and challenges, known failure modes, because we've seen these in past incidents, or we think that we will in the future.
Okay, so the key thing about robustness is it's about responding to known hazards and challenges and being able to respond effectively to those. Okay.
Yeah.
Okay.
We'll talk about some examples once we've gone through them, I think, and that will help.
Sure. And then there's resilience, which, how is that different?
Yeah. So resilience is the capacity of the system, the socio-technical system that is, to adapt to unanticipated challenges or hazards. So that's emergent challenges, unknown unknowns, things we haven't faced before that we didn't think could or would happen, or just things that we hadn't ever anticipated. So resilience helps us respond to those unanticipated challenges in the future, reducing the impact where the system was not perfectly robust. So resilience is something that the system, the socio-technical system, does, not what it has.
Yeah. To me, it sounds like I've seen a lot of work in the realm of robustness, but not a lot of conscious work in the field of resilience and in the places that I've worked in the last 16 years.
Yeah, absolutely. And probably what's unhelpful, I think, in software is that often we use the term resilience when we're talking about things that, according to these definitions, would be robustness, like work about improving robustness. So I guess kind of the key thing is we can't predict every possible challenge or failure mode that a system will face. So a system can't ever be perfectly robust or perfectly reliable. That's kind of when resilience engineering comes in. And resilience helps us understand what forms of robustness to implement, which in turn contributes to improving reliability. But we need resilience. That's the kind of key thing.
I think it's John who's mentioned somewhere. I don't know where exactly, that there's just so much resilience everywhere, but we don't really think about it because there's so many software systems, complex systems all over the world that are working most of the time pretty well because there is just resilience there, because that's just the nature of people. We find ways through things and to solve problems and become more responsive to the unknown.
Mostly in resilience engineering, we try to recognize and capture instances of resilience and resilient performance to kind of extend and expand this. There is one paper that is kind of a complete capture of actually engineering resilience, and it's called Building and Revising Adaptive Capacity, Sharing for Technical Incident Response, a Case of Resilience Engineering.
Okay, so as you mentioned before, we've got some examples of reliability, of robustness and resilience, which I think will help me understand as well. Do you want to run through what's an example of like reliability or robustness to start with?
Yeah, so let's say we have a theoretical team that looks after an internet-facing web application. Maybe it's multi-tenant SaaS, or maybe it's like online quote and buy for insurance. This internet-facing web application experiences a kind of a huge and sudden load spike. The team has experienced this before, And previously, they've implemented dynamic and responsive scaling, rate limiting, some other stuff. So when this has happened, the system has been able to handle that huge load spike. So in that instance, we can say that the system is robust to that hazard. And kind of in hindsight, after that kind of instance, we can say that the system was reliable.
Okay. And so in that case, it was robust to that because the team who had built this foresaw load spikes. It was like a known thing that would, a hazard that could occur, and they prepared for it.
Either foresaw or they experienced it in the past and couldn't handle it, and therefore did that work.
Gotcha. Okay. The resilience.
It's a little bit harder. So let's just say one day this internet-facing web application experiences a third-party failure or a vendor failure, and that blocks their responsive and dynamic scaling capability. That failure to them is unforeseen. It's not something that they ever thought could happen. However, because the team has done so much work on robustness based on past incidents, maybe they've also been doing chaos drills, they're able to work together to figure out a workaround, implement it, and enable their system to recover before the vendor resolves their issue. So that sort of thing is an example of like resilience of the system, the socio-technical system. I think the key details for resilience is it has to be unforeseen. So a situation not yet imagined, and the capacity to adapt relies on capabilities that existed before the event.
Would it be fair to say that to have resilience, it's about people?
Yes, yeah, 100%. It's about human performance.
Right. I'm not going to even open the can of worms of saying, but what about AI? Can you have a resilient AI system with that?
I feel like AI and resilience is like a whole separate episode for you.
Yeah.
Yeah.
Okay, I understand that. That makes sense to me.
Yeah. Probably some like key kind of, I suppose, clarifications. Resilience isn't a synonym for like redundancy. Robustness I've already talked about. It's not a synonym for high availability or fault tolerance or chaos engineering. It's not to do with software or hardware, right? So as you said, it's about people. It's about the socio-technical system.
I don't know. You've articulated for me something I've felt for quite a long time, that at the end of the day, stuff is going to constantly happen that you can never be prepared for. So the best thing you can prepare is that as a group of people, you build, the ability to work together well, domain knowledge and understanding. You practice in different areas so that when other things happen, those skills still help you adapt to different, to problems of other areas, and also having the right culture. So there's that, collaboration and trust. Because if things, really intense things happen which aren't expected, a group of people who trust each other, I think, and have that right, I don't know. The ability to collaborate really well and effectively and with that high trust environment, I think, has got to be a good thing, as opposed to...
Yeah. What you said at the start there is really interesting. A couple of months ago, I was having a conversation with the CTO at a client that I'm working with, and they'd recently had an incident of the kind of like, please explain variety. And what he said was something like, come to the end, like I'm starting to realize that I can't stop incidents from happening. Like they just need to be managed when they do happen. And I was like, ding, ding. Yeah, it was really great to hear. Kind of like that. And it's kind of we're going to talk about a bit more.
The next thing we were going to talk about, and this is really important for me because I've struggled with this, is we talk about complex systems, or I often say complex distributed systems as well. And I talk about it all the time at work, and I'm trying to explain that the domain that we are currently working in is so vastly complicated that it's impossible to control it and to predict it. And I still get these blank stares. I feel like I'm not describing it very well. So maybe you can help me with the way that I talk about complex systems. So what's a complex system?
So I think when trying to understand resilience engineering, that shift in thinking is required. And for me, being able to articulate what a complex system is really helped. But there's like another lens, which is the safety 1 and safety 2 type kind of lens, which we'll talk about as well. So complex system, I really like Laura Nolan's definition from her talk at LFI conference in 2023. So the talk was called Systems Thinking for Incident Analysis. And this is the definition. So This complex system has multiple components, nonlinear interactions and feedback loops, interactions with environment, so like the internet, users, malicious actors, vendors you rely on, kind of all sorts of stuff going on there. It is dynamic and constantly changing. I think that dynamic and constantly changing one is really key to think about. Complex systems have state and history, and problems often arise in the interactions rather than the individual components themselves. So the interactions and integration points.
Yeah.
You also can't really talk about complex systems without mentioning How Complex Systems Fail by Dr. Richard Cook. Can't really talk through that now, but people should have a read of that.
It sounds like any organization of any kind of scale at all is going to be full of, or like at its core, is going to have a complex system or systems.
Yeah. These days, I think of like companies and organizations, if they aren't a technology like business or technology company, they are technology driven and technology enabled. And so, yeah, they all have complex systems. So from my perspective, the most important aspect when thinking about complex systems is that they're dynamic and constantly changing. Fred Herbert, who is a staff SRE at Honeycomb, summed it up really nicely in this quote. People have a mental model where the system is stable until disturbed, far more often than they have one where the system is balanced because it is constantly intervened with. So the latter is a much more useful approach to thinking about complex systems.
It made me think about, and this is going a little bit off topic here, the whole thing that there are certain orgs who still want to only release change like once a month or once a quarter because they want to keep it in a working state. Although there's change freeze windows for like 2 weeks. Oh, we don't want to, because we don't want any change because it might screw things up. Whereas, does that really improve like safety? Does it make things more reliable in the end of the day? I don't know.
I think stuff like that to me is all about the illusion of control. This kind of like idea that you can control the system to make it reliable and stable, but you kind of can't. Like you say, there's a rabbit hole we could go down there. Like different organizations are at very different places on the spectrum of like continuous delivery and their ability to deliver change safely. And so there are definitely some organizations that probably have a lot of work to do. And so some of those methods feel like they work because of that. But I think there's kind of a point that you cross, like a threshold, and change freezes and stuff like that become not helpful.
So I think that flows quite nicely into the discussion about safety 1 and safety 2. And is safety 1, okay, I'll have a go without looking at the notes. Is safety 1 about that the idea that there's a system and you want to try and control it to stop the bad things from happening, and that's no, I'm not going to.
Not really. So Eric Holnagel was responsible for this idea of safety 1 and safety 2. And so my understanding is that he wanted to point at it and highlight what makes resilience engineering different by using the contrast. So he labeled it safety 1 and safety 2 on purpose. So safety 1 is about kind of reducing failure, as few things as possible go wrong. It's a bit of a focus on human error, and humans are a liability or a hazard. Accidents or incidents are caused by failures, malfunctions, and we learn predominantly from things that go wrong. Safety 2, on the other hand, is about increasing success. As many things as possible go right. So focus on human performance. So the system succeeds because of humans and their expertise, their ability to monitor and observe the dynamic complex system and learn, adapt, and respond as needed. When it comes to an incident, we want to understand how things usually go right as the basis for understanding how things occasionally go wrong. What were the conditions for variability in system performance?
Is there value to safety 1? Or is the intention behind this to say safety 1 was the way we have been doing things, but here's a better way?
Yeah, so it's to highlight that contrast and help that shift in thinking towards resilience engineering. So there's 2 kind of key papers, I think. So Tale of Two Safeties and From Safety 1 to Safety 2, a white paper, which I think are both by Eric Holnagel. So they kind of explain it in a lot more detail. Another kind of potentially more accessible explanation. There's this talk called Resilience, It's Not You, It's the System by a doctor in the New Zealand health system. And it actually provides quite a nice explanation as well.
Yeah, there's going to be a lot of links in the description of this episode. So jump down and look at the articles, look at the videos, and yeah. Interesting. I have, okay, so I'm just reflecting here. I don't think I've ever seen a deliberate attempt to implement safety 2 in my career.
Oh, that doesn't surprise me. I think it is happening in pockets. I think one of the biggest challenges with resilience engineering work is when it is happening. If it's happening at all, it's happening kind of off the side or someone's desk or via guerrilla tactics, and the work is often not kind of legitimized. I think that's one of the biggest challenges that we have, to get the kind of concepts and work and value understood and legitimized so that we can really dedicate effort towards it.
It feels right to me. Like there's a rightness to it. I was like, yes, that's the way we should be doing things. I don't even know why. It feels...
Well, I think as the classic system thinker, like that's a big factor. I think that's why for me it just kind of all slotted into place. I remember when I first started learning about resilience engineering, I started thinking back in my career, and I remembered like a long time ago, I used to do like data center migrations and infrastructure upgrades. And I remember having like quite a gnarly kind of incident doing an infrastructure upgrade one weekend where we took out quite an important system. We got quite close to like a like regulatory reporting like threshold. That was sort of a big deal. And that's my first time where I can remember doing something that looked like contributing factors, because we did our own retrospective as a team before we kind of rolled up to our post-incident review with various stakeholders. And this is kind of classic resilience engineering story, but we presented like all of the systematic factors in the incident, all of the safety nets that should have caught us, but like kind of all of the other things that kind of just didn't go our way. And so many things kind of had to go wrong for us to have that incident happen that way. And that's kind of the point. And that was in probably like 2015 or something like that, 2014. And I, had no idea about any of this stuff at the time. But that was what made sense to me.
And what was the reception to explaining it that way? Was it well received?
I remember there was a lot of quiet, like just stumped, just like, okay. Like, because I presented it, I like kind of tried not to make it defensive and just factual. Yeah, and I just remember a lot of quiet. Like, what did we just listen to? It was right at the time of like kind of the DevOps transformation at that company as well. So it was, I think it was interesting from that perspective.
You mentioned before about having to change our sort of mental model. What do you mean by a mental model?
What do we mean by mental model? Something we talk about a lot. Yeah, something we talk about a lot in resilience engineering. So a mental model is an internal representation or framework that an individual, so an engineer, uses to understand and interact with the complex system. So it helps them make sense of information, interpret situations, kind of predict outcomes, decide what kind of actions to take. Our systems are constantly changing over time. So it was Dr. Gary Klein who said something like, mental models are stories, not pictures. So they have a time dimension. So when we think about a mental model of a system, it's useful to think about them as something that is continuously evolving rather than being static. I guess if you want to step into that concept a bit more, there's the above the line, below the line kind of diagram by Dr. Richard Cook. So we have above the line of representation, and below the line. So below the line is the system, but engineers never actually touch it or see it. You interact with representations of the system. So that's what's above the line, those representations and interfaces. So how an engineer understands the system, their conceptual understanding, it's about their mental model and then using those representations and interfaces. So above the line is where that kind of thinking, understanding, and problem solving happens. It's where cognitive work happens. Another kind of good kind of thing to look at for that is how your systems keep running day after day, which is a talk by John Allsper, kind of explains that. well and in quite a lot more detail.
It makes me think also different people kind of conceptualize or think about the world in different ways. I know some people who are very visual and can remember, they can picture things in great detail in their minds. Some people can't. I'm very geometric. I'm always thinking about things in terms of shapes and angles and lines, and how that must shape the way that we work on systems, because we're conceptualizing them in different ways.
Yes. So I'm very visual. So yeah, I totally understand that. I think the thing that's really important about mental models is we don't want everybody to have the same mental model, because like you said earlier, it's impossible to understand the entire system. So what we want is engineers to have their own mental model of the system, and then through kind of resilience engineering and incident learning, we want to compare and contrast those mental models and update them and kind of grow them and improve them as this constantly changing complex system evolves. Mental models need to as well.
So I think I just had a mini breakthrough.
Well, observability is a thing that you're quite into, right? So if you think about like you're using like monitoring dashboards, metrics to make inferences based off your mental model.
I think I've come into conflict in the past with people who have, they think about the world in terms of words. And so they write a lot, and probably it's amazing, but my brain just can't comprehend it. I know we're going off topic again here, but because I'm more, like I said, visual in a geometric sense, and so I'm always going away and drawing diagrams to represent the things that people have written, and they get frustrated, like, why, I've already written it, And I've had that kind of conflict in the past. So I bet that kind of thing happens all the time across the industry from different people.
Yeah,
who have different ways of thinking.
My approach for stuff, so I struggle with either really verbal or really written stuff, and I just need time to think about it. And I'll just say to people, I need some time to think about this, because like my brain just needs time to process and catch up. Maybe draw some pictures. So I've got a picture over here that I drew while trying to figure out how to draw a picture. Yeah.
The next topic was human error, and I'm going to sort of guess and go ahead here that traditionally when things go wrong, we've often attributed that to a human being has made a mistake and that has caused this thing to happen. But everything that we've talked about so far has been more about the system. There are, the system isn't resilient.
Yes. Yeah. So I think one of the key themes we see that is important to call out is this acknowledgement that the idea of human error can't really be considered a cause or an acceptable conclusion. So human error is an indicator of underlying issues in the wider system that need to be further investigated. So human performance is systematically a result of an engineer's tools, technology, goals, and operating environment. It's not the human in isolation making a mistake. You've got to look at the whole system. And this thinking around human error came before resilience engineering, but it is related. This idea that human error is kind of not helpful when thinking about complex system failures actually came out of the 3 Mile Island nuclear reactor accident in the US.
Oh, what? Just playing devil's advocate. What if there's an incident that's caused because someone is being malicious? Is that but that's not really human. That's just someone deliberately to sabotage.
Yeah, I mean, is that error? Because that sounds intentional.
Yeah, true.
Yeah. When we think about human error, there's kind of 2 books. So Behind Human Error, which is by a collection of authors that includes like David Woods and Richard Cook, Sidney Dekker, and Layla Johansson, I think is how you say it. But there's also Sidney Dekker's book, The Field Guide to Understanding Human Error. So they're kind of good ones to have a read of that talk a bit more about that in the context of like accidents or incidents. I think everyone who's involved in incidents has probably heard something like, why didn't they respond to do X, or why didn't the engineer know to do Y? And so those are really great examples of human error view of things. But they're also examples of kind of hindsight bias and counterfactuals. So a counterfactual is counter to the facts. If they had done this, things would have been different. It's a reality that didn't happen that doesn't help us understand the incident. Hindsight bias changes how we look at past decisions and actions. So it takes something that was very complex and difficult at the time and simplifies it into something very linear and uncomplicated. So when people know the outcome, they overestimate their ability to predict and prevent the outcome. The tunnel analogy is often referenced here from Sidney Dekker's book. So we want to understand how people's actions made sense at the time, given their goals, their context, and knowledge, and what they were paying attention to. So we need to understand the perspective from inside the tunnel, but we need to pair this with the wider organizational context, the wider system context, if you will. So last year I was in a really complex incident. It was a metastable failure of the cascading failure variety. There were lots of responders were saying things like, this just doesn't make sense. There's lots of cognitive dissonance. The incident itself had a lot of contributing factors. So there had been cost-saving pressures that led to changes being made to auto-scaling, and that was kind of a contributor. There were a number of known legacy patterns that enabled that like quite gnarly and complex cascading failure to occur, plus kind of a number of other things. So saying, why didn't they do X, which is something that we kind of happened around this incident, is a total oversimplification. It avoids examining how your own past decisions might have contributed to the conditions that enabled the incident to occur.
When I first hear that kind of thing, like, why didn't they do X and that? You think about sort of blame and politics and that kind of thing. But I also think that a lot of people struggle, and I do, I get worse over time, with slow thinking, with really stopping and being really analyzing a situation in great detail and giving yourself the space to go deep and wide and to really make sense of something in context. I think maybe in some cases it's just a matter of not being willing to do that level of thought and analysis. And it must just be because of this. That's because that's right in front of our face and easy. Yeah.
Yeah. I think it's important with resilience engineering to acknowledge that there's a lot of like accepted behaviors and practices that are really deeply embedded and ingrained in our industry. And what we're talking about is kind of going against all of those. So it's quite a significant shift. So like where maybe people have historically made quite quick conclusions. I say historically, but in a lot of contexts, people are making quite quick conclusions about incidents. Like we're kind of saying, actually, maybe don't do that. Let's take a minute to look at things kind of more deeply and more broadly. So those sorts of questions, why didn't the responder do X, or why didn't the engineer know to do Y? They don't acknowledge a lot of what we know about complex systems. So I personally have never done this, but Sean Klein, who is the technical program manager for modern incident analysis at Microsoft Azure, it's a thing that he does or has done, which I kind of like to think of as the post-incident review after party. So you do your PIR, but then you read how complex systems fail and figure out how many things from that article apply to the incident. You can do it together or can do it by yourself, but it's basically like, I guess I know that Sean has done it as an introduction to resilience engineering concepts and start to bring people kind of around to this way of thinking and kind of help start that shift.
That's really cool.
Yeah.
All right. So wrapping up, last topic, learning from incidents or incident learning. Yeah.
So one of the key areas we focus on in resilience and software is learning from incidents. So typically we see this idea of like blameless learning as a token afterthought. The point of like a post-incident review is to agree a version of events and agree actions. So most often this is making a very complex system and a complex set of factors very linear and oversimplified. And it's insufficient for actually improving the system. Colette Alexander recently did a talk with the DORA community on resilience engineering. And she articulated it really in a way I really liked. So she said, instead of what is the root cause of how this perfect system broke, try what contributing factors were at play in making the system move into this failure mode. She extends on it more from a resilience engineering perspective. I think that is like a really good kind of just starting point for why we want to look at learning from incidents.
It reminds me of the previous episode I just released. It might be a few behind after this one. Andrew Hatch talking about not thinking about an incident rather like a tree as opposed to a linear root cause, but there's a tree of different contributing factors.
Yeah, I really liked that episode, and I liked that Andrew kind of referred to root cause as like rather than being wrong, like kind of just not suitable for what we're doing. Yeah, I liked that. So people like Andrew, people who are practitioners in resilience engineering, drawing on techniques from incident analysis from these higher consequence industries to really deeply understand and learn from these events. So it draws on things like naturalistic decision making, cognitive task analysis, and sense making, looking at mental models, cognitive work, using this new view of human error and stepping away from hindsight bias and counterfactuals. So in the words of John Allsper, it's the richest understanding of the event for the broadest possible audience. So we have to start taking human performance seriously in our industry. So we are ever more dependent on these software systems of increasing complexity. So we want to build systems that are reliable and robust, and we need our socio-technical system to be resilient. We need to be able to continuously adapt. So ideally, we want to better enable engineers and system operators to compare and improve and grow their mental models for these massively complex and constantly changing systems. We want to enable better decision-making for engineering leaders, improve both the robustness and resilience of our systems and our organizations.
Yeah, I mean, it sounds silly to say it out loud now, but I think so much focus has been put on, the reliability of the tech itself. And I just really like the focus on people again. And, technology can't be resilient. That's really by itself. It needs people. Yeah. And I think that building the conditions for resilient socio-technical systems probably has lots of other benefits beyond just how you manage with incidents, but also, happier people and probably delivery of products and better quality products and those kinds of things as well.
Yeah, I mean, absolutely.
And you've got a couple more resources that you thought people might want to look at. What were they?
Yeah, so I think if you want to get started on learning from incidents, there's the Howie Guide, which is by Nora Jones, Laura Maguire, and Vanessa Huerta-Grande. But there are some other resources and topics that people should look at. So Lauren Hochstein has a resilience engineering, where do I start kind of page article. It covers a lot of what we've talked about and kind of links out or provides more detail. It also covers some things that we haven't kind of covered, like automation and coordination, Rasmussen's dynamic safety model. There's also the Stellar Report. So it's a consortium that looked at how engineers and tech companies deal with complexity and incidents, which is worth reading. Come and join the Resilience and Software Foundation Slack. And there's lots of people in there learning, doing, sharing. So it will be really good. And you could also listen to the This Is Fine podcast with Colette and Clint, if I'm allowed to shout out another podcast. But
of course, sure. Yeah. Thank you so much, Michelle, for pulling all this together and putting together what I think is a really nice, cohesive introduction to resilience engineering. And there is going to be a lot of links in the description to other resources that if you're out there listening to this, that you can go and read further about any of these topics. I think this is like bringing the podcast to another level in terms of the detail and sort of thought that's gone into it. So yeah, thank you so much. And Michelle is writing a blog. You want to tell us anything about it, or
it's currently called the Untitled Paradox blog, but it's about the paradox that we face in resilience engineering. It's kind of what I'm trying to write about. But yeah, thank you so much for having me and for the opportunity. I think this is really important. This is really great to have the opportunity to kind of frame up a good kind of thorough introduction to resilience engineering and have that out there.
Yeah, and I am actually really looking forward to when I edit this, going through the resources properly and going deep in myself and finally join the Slack community. My goodness. Every time I hear Colette and Clint talk about it, I make sure to join the Slack community. I'm like, yeah. And then it goes out of my mind 10 minutes later. But yeah. Thanks again, Michelle. And to everyone else at home, I hope that you have a wonderful week, and I will see you next time.